Welcome to this webinar by Applied Parallel Computing. I'm Juraj and I will present you advanced aspects of CUDA. In this part, we will talk about efficient data transfers between host and device or between multiple devices. We will see properties and implementation of PCI Express communication bus and how various memory types influence transfer bandwidth and latency. We will have a closer look on performance of unified virtual memory, which was introduced in CUDA 6 and supported since Kepler architecture. In the last part of this data transfer section, we will introduce CUDA streams that are necessary in order to utilize parallel data transfers. It is important to understand what impact does data transfers have on overall application performance. In this setting, we have CPU and GPU, each having its own memory space with solid memory bandwidth. Obviously, the weakest link is the interconnection between CPU and GPU. PCI Express of second generation provides bandwidth of 8 GB per second in ideal case. But we will see that actual bandwidth may be even lower depending on the overall architecture of the compute node. You will learn properties and some good practices regarding the host-device data transfers. It is useful to realize when the data transfers between CPU and GPU are performed. Obvious answer is that data transfers are performed when transferring input and output arrays between CPU and GPU. But there are more events that involve communication. First of all, it is transfer of binary code to GPU, passing kernel arguments such as block size or amount of shared memory. Communication is also performed when transferring return variables or initializing device variables. PCI Express is computer expansion bus that provides point-to-point connection on logical level. Each logical interconnection consists of multiple lanes, and when there are multiple processes requesting PCI lanes allocation at the same time, total amount of lines is divided between processes, which limits the effective bandwidth per process. Single PCI lane is full duplex line with transfer rate of 500 MB per second in both directions. PCI Express of second generation can assign maximum of 16 lanes with peak transfer rate of 8 GB per second. We have seen that Kepler and Maxwell architectures are using PCI Express of third generation that doubles the peak bandwidth of previous second generation. The next gen PCI Express bus has been already announced with release date in late 2015. It will double the performance of the current PCI Express generation, reaching bandwidth 31 GB per second. Also, this is the Tesla GPU, and this part over here are the PCI Express pins that allows the GPU to be connected to the host system. This is the result of PCI bandwidth test, where packets of different size are transferred over PCI. It is important to realize that we reach full bandwidth only from some reasonable size of transfer data. Reasonable bandwidth is reached from the data size of approximately 500 kilobytes. Therefore, it is better to pack all data into one package and send all at once, rather than sending individual small chunks of data between host and device. In this test, we also see performance difference between regular memory, depicted in blue, and pinned memory in red. We will discuss properties of these memories in the following part. PCI Express is shared between multiple peripheral devices and multiple processes, so the effective transfer rate varies depending on the PCI lane's availability for our process. We see that in one case, our process gets allocated 9 lanes, reaching bandwidth of 4.5 GB per second. And at some point, it gets guaranteed extra 3 lanes, summing up to 6 GB per second bandwidth. You cannot influence this behavior as the application programmer, but you should be aware of this, especially in case you will be building your own GPU cluster. So you already know that CPU and GPU have their own physical memory spaces, as well as different GPUs have their own global memories. That means we have to migrate our data between the nodes as necessary using the weak PCI Express link. In the following part, we will inspect various data transfer types and see if there is some possibility how to boost performance of these data transfers. So we will discuss following data transfer types. First of all, it is pageable and pinned or page-locked memory transfers. Then we will see explicit and implicit data transfers. We will also inspect the performance of the unified virtual memory. We will have a look on data transfers between GPUs within the same host and GPU communication over the network interface. And finally, we will inspect non-blocking asynchronous data transfers. First of all, let's have a look on the difference between pageable and pinned memory. When you allocate memory in a host code, the allocations are pageable by default, which means it may be swept to disk. So your data may not be present in a physical memory when the transfer to device is requested. On the other hand, pinned memory is allocated within the kernel memory space, depicted as this part of memory space, which cannot be swept, therefore such data are always physically present in the memory. When a regular memory transfer is issued, an allocation of page-locked memory is necessary, followed by a host copy from regular memory to the page-locked one. Afterwards, the transfer takes place, host is blocked and waits for the transfer to be completed, and then performs the deletion of the page-locked memory. This consumes host time, which is avoided when directly using page-locked memory. Please note that the GPU memory is automatically allocated as page-locked, since the GPU memory does not support swapping to disk. There is no need to do any special memory allocations like in CPU case. In our PCI Express bandwidth benchmark, you can see that pinned memory transfers achieve higher peak transfer rate than a transfer rate of regular memory. In general, this is because we avoid additional implicit mem copies within the host memory. We also have more realistic benchmark, a simple stencil code that computes wave propagation. Basically, it contains 4 core activities, that is transfer of data from host to device, kernel compute, backward data transfer to host, and some finalization of computation on host. In this case, we used regular memory, and in the other case, we used pinned memory for data transfers. Also, in this benchmark, we observe slightly better performance, especially of transfer from host to device. Pinned host memory can be allocated by API function CUDA malloc host, as opposed to regular host memory allocation using standard C function malloc. CUDA malloc host takes 2 arguments. It takes size of the requested memory and returns pointer to allocated memory, similar as CUDA malloc that allocates memory on the device. Take-home message about pinned memory should be that it usually performs better as regular host memory. We have seen that in both benchmarks we have reached a higher bandwidth of data transfers. However, you should not over-allocate pinned memory, since it reduces amount of physical memory available for kernel of the operating system. In such cases, the system could become unstable. In this part, we will inspect performance of the unified virtual memory introduced in CUDA 6. Unified virtual memory is an abstraction of host and device memory on programming level. Developer views the memory as if there is only one shared memory between host and device. On the hardware level, there are of course 2 distinct memory spaces, as we have seen in previous sections. Unified virtual memory simplifies developing or porting of your applications to CUDA. As you see, without the unified virtual memory abstractions, you explicitly need to declare 2 distinct memory spaces for your data and manually manage all the data migration between host and device. In case of unified virtual memory, all these transfers are managed by CUDA engine. You can request for virtual memory by API function CUDA malloc managed, and use the memory in kernels or in host functions as needed. Let's inspect the performance of this memory feature in CUDA. Let's assume the use case where we want to load and initialize data on host, use it in GPU kernel to compute wave propagation stencil code, and finalize the computation on host to compute some statistical properties. This will require two data transfers. First, host to device transfer, followed by kernel launch, backward device host transfer, and finally the host computation. We have already seen the performance of this application using explicit data transfers with regular and pinned memory. The performance of virtual memory is significantly degraded. This is because the data migration, managed by the CUDA engine, is performed in multiple smaller transfers when data are accessed from host. This introduces a lot of latency and also achieves poor bandwidth. That's why the blue portion of the figure, corresponding to device to host transfers, is so much greater than explicit memory transfers, where the data are transferred all at once. Performance of the virtual memory in the other direction, that is host to device, is comparable with explicit memory transfers, since we do not observe this problematic behavior. However, the unified virtual memory still performs better than old memory mapping system known as zero-copy memory. In this case, memory is always present in the pinned host memory. If kernel uses such memory and requests access to some portion of it, data are always transferred from host, even if requested multiple times from kernel. One further performance issue with unified virtual memory is that it implements critical section to access memory. In case we use multi-threaded host application, the threads requests to access memory are serialized, resulting into performance degradation. In case of serial CPU code, UVM is 1.7 times slower, but in case of multi-threaded code, the UVM is 4.5 times slower than explicit memory. To sum up this section, the unified virtual memory simplifies programming model, but has performance issues in case of device to host transfers and in case of multi-threaded applications. However, it is still good in a sense that it simplifies GPU porting, allowing you to omit explicit memory copies during intensive GPU kernel's code development. Following part will discuss peer-to-peer data transfers. Peer-to-peer data transfer is transfer between two devices located within the same shared memory server, so that communication can be performed over PCI Express and not going through network interface. Peer-to-peer allows us to copy data directly from GPU 0 to GPU 1 without allocating and staging memory for host. Peer-to-peer data transfer thus reaches high bandwidth that saturates PCI bus. Without peer-to-peer technology, we would have to first copy data from GPU 0 to host, and only from host copy it to target GPU. Another feature possible thanks to peer-to-peer is direct access. We can access data located in a GPU 1's memory from kernel running on GPU 0, without explicitly copying data. Such data are cached in L2 cache on the target GPU. In this case, that would be GPU 0. Peer-to-peer feature is possible thanks to second generation of GPU Direct and unified virtual addressing. Unified virtual addressing was introduced in CUDA 4 and supported since Fermi architecture. In a regular cluster node, we have devices connected to PCI Express, each having its own memory space. If we use data pointer in our code, which is basically some data address, it can physically exist in all memory spaces, either host memory or in one of the GPU's memories. In such case, we need to specify direction of the memory copy, the fourth parameter in CUDA memcopy, host to device, device to host, or device to device memcopy. With unified virtual addressing, all the addresses are mapped to a single address space. Note that individual memories are still physically separated, only logical memory addressing is continuous. In such case, we can do all our memcopies without specifying its direction, which will be identified automatically, since destination address can exist exactly once within the server. Here you see code of peer-to-peer transfer. In this example, we allocate some memory on both of our devices, enable peer-to-peer access, and copy data from GPU 0 to GPU 1. Note the last parameter in CUDA memcopy, that is CUDA memcopy default. Since CUDA engine can determine that GPU 0 buffer lies within the GPU 0 address space, and the GPU 1 buffer lies within the GPU 1 address space, we don't have to specify any more information regarding the direction of memcopy. You can also use this option instead of CUDA memcopy host to device or CUDA memcopy device to host, in case your server supports UVA. However, it is good programming practice to specify the transfer direction. To sum up, we have seen that peer-to-peer and a unified virtual addressing can be used to both simplify and accelerate CUDA programs. Unified virtual addressing maps all the memory addresses to a single address space, which enables CUDA engine to determine physical memory location from pointer value. It simplifies library interface, for example CUDA memcopy, and enables us to copy data between GPUs with less overhead. That is, data can be copied directly from one device to another and not staged through host memory. Now let's have a look on communication between GPUs over the network interface. Second version of GPU Direct, together with unified virtual addressing feature, allowed to implement peer-to-peer data transfers. It used high-speed direct memory access transfers to copy data between the memories of the two GPUs within the same node. Third generation of GPU Direct uses remote direct memory access transfers between GPUs and other PCI devices. That enables us to send data between GPUs on different cluster nodes. Consider we want to transfer data from one GPU to target GPU located within a different network node. Without GPU Direct feature, data would be transferred first to CPU memory of current node, then to driver memory of network card. Data would be sent over interconnection network to network card controller of node 1, copied to memory of host in target node, and only from there transferred to memory of target GPU. GPU Direct eliminates unnecessary system memory copies, dramatically lowers CPU overhead, and reduces latency, resulting in significant performance improvements in data transfers. GPU Direct is also essential requirement to utilize CUDA-aware MPI. In previous two sections, you have seen that efficient data transfers could be achieved by using write technologies. However, in some cases, using write underlying technology isn't just enough. You also need to use write programming features. One of such are asynchronous data transfers that enables you, for example, to hide communication latency by overlapping communication by computation. Regular CUDA memcopy is blocking, so it will block host until the transfer is complete. On the other hand, asynchronous CUDA memcopy is not blocking, so that the return from this function is immediate, and you can utilize CPU with some useful computation while data are being transferred. There are two additional requirements for asynchronous memcopy. First is that the transferred memory has to be allocated as pinned, so that no page faults occur during the transfer, and the whole transfer can be realized using DMA feature independently on the CPU. Second is that you need to specify CUDA stream. Basically, stream ID is just a number that specifies sequence of some CUDA operations. Operations from different streams can be performed in parallel. Since the asynchronous memory transfers are not blocking with respect to host, CPU can use its time more efficiently, rather than idling in case of synchronous data transfers. CPU can issue the memcopies and kernel call, and while data are being transferred, or kernel is running its computation, CPU can use all this time to compute something useful. In case with used blocking memory copies, only the kernel call is asynchronous with respect to host, so only this portion could be overlapped. There is no speedup when compared to blocking data transfers. We only utilized CPU. With asynchronous data transfers, it is possible to overlap communication and computation, as you can see here. Using this technique, you can actually achieve some speedup. But in order to write this code, we first need to introduce CUDA streams. Here you see basic example of asynchronous data transfer. We allocate pinned host memory with CUDA malloc host and pass this data to CUDA memcopy async. CPU issues these three operations in asynchronous manner. So while the memory is being transferred or kernel is being computing, CPU can continue its own computation, in this example in function f. CPU will get blocked only on CUDA device synchronize, which will block until all previously issued GPU operations are not finished. Here you also see stream ID, which is the last parameter of CUDA memcopy async, as well as the last parameter of the kernel call. In this example we used default null stream. Let's get back to our example and see how you can overlap communication with computation. You can do this using CUDA streams. Stream is a sequence of CUDA operations that execute in issue order on the GPU. You might not be aware of that, but you have already used CUDA streams. If you don't specify CUDA stream explicitly, all CUDA operations are put to default, so-called null stream. For example, regular CUDA memcopy or kernel launch without specified stream. That's why CUDA memcopy will execute only after kernel that computes data to be transferred, even though kernel launch is always asynchronous. These operations are located within the same default stream, and from definition of CUDA stream, operations execute in issue order within single stream, even though kernel launch is asynchronous with respect to host. Therefore, if you put different CUDA operations to different streams, they may run concurrently. And this is exactly how we achieve the memory latency hiding by overlapping it with computation. This is a simple demonstration of the asynchronous CUDA memory transfers and usage of CUDA streams. First of all, you need to create the streams. In this code example, we create two streams using CUDA stream create function. What you need to do next is submit work to these streams. CUDA memcopy async takes stream identifier as last fourth parameter. CUDA kernel launch similarly takes stream identifier as fourth parameter. First two are well-known number of blocks and threads within each block. Third parameter is amount of shared memory per block, and last parameter is stream ID. Operations in one stream will execute independently of the operation in the second stream. At the end, you should not forget to destroy the streams and free related memory. When the work has been submitted to CUDA streams, CPU can run its own computation independently on GPU, in parallel with operations from both streams. Only CUDA device synchronize will block until all the GPU operations are not finished. There are cases when you need to synchronize operations within different streams. CUDA offers you multiple levels of control. CUDA device synchronize blocks until all previously issued operations within all CUDA streams for given GPU are finished. CUDA stream synchronize blocks until all previously issued operations from given stream are finished. And finally, fine-grained synchronization is provided by CUDA events. Stream 2, identified by CUDA stream wait event, will be blocked until stream 1, specified by CUDA event record, reaches the given event. Event is basically an empty operation in some stream, which can be used for synchronizations or for measuring execution times and so on. Following operations are implicitly synchronized, therefore no barrier is needed. All these operations have the same effect as CUDA device synchronize. To conclude this section of efficient data transfers, we have seen how does PCI Express work, that it can be shared by multiple users or processes, and therefore the peak bandwidth gets limited. We have also seen that PCI Express is efficient only starting from some reasonably large data buffer. In the next part, we have inspected performance of the unified virtual memory. It simplifies programming model and may be convenient to use it during rapid porting to CUDA, but its performance may be worse, especially in case of device-to-host transfers, where data are transferred in small chunks. It's always a good idea to know when underlying runtime routes data through intermediate buffer and avoid it. For example, by using pinned memory or deploying GPU direct technology in your server. And the last point, regarding the asynchronous memory transfers, is that it's always a good idea to compute something while data is being transferred. In this way, you can efficiently hide memory latency in your applications. In the last part of this webinar, we will inspect profiling tools that are especially useful when optimizing your applications and you need to discover the bottlenecks and the most time-consuming operations. We will also have a look on two debugging tools, that is CUDA GTB and CUDA memcheck.